Well, as you might have guessed, we are going to return to information theory and look at machine learning from that perspective. We're transmitting signals consisting of features, words or other features, for example, and we are using those to predict the values of some behavior, browsers versus buyers, etc. And our goal is to improve the mutual information between these two signals via a machine learning algorithm. Now, what you all are probably waiting for is the actual definition of mutual information. So the mutual information between a feature, a word for example, and a behavior, browser or buyer for example, is defined formally as the probability of that feature and behavior occurring for some particular value of f and b multiplied by this quantity. And this sum is a double summation over all values of feature and all possible behaviors. So in our case it would be 4 values in the sum: feature present, absent, behavior, browser, buyer, and in each case you would compute the joint probability of a feature and a behavior multiplied by this ratio. Now, to understand this ratio better, imagine if the feature and behavior are independent. If that's the case, then the probability of the feature and the behavior together is nothing but the product of the probability of the feature times the probability of the behavior. So this ratio becomes 1, the logarithm becomes 0, and so does the mutual information. If the feature and the behavior are independent, then obviously it's hopeless to try to predict the values of the behavior from the values of the feature. We'll do an example in a minute to actually compute the mutual information. But before that, a little history about mutual information. What Shannon was really trying to do is measure the information content of various signals. So there's a formal definition of information content called the entropy, which we again haven't defined, and we're not going to do that. But still, believe me, there is one, and similarly there'll be an information content for the behavior signal. There'll also be an information content for the signal consisting of both observations, the feature and the behavior combined, and the mutual information is nothing but the difference between the total information in f and b and the information of f and b when observed together. We won't go into the intuition behind this too much, except to note that the information content of two variables together than the total information in both the variables put together. As a result, the mutual information has to be positive. Just remember this: if during any of your calculations you get a negative value of mutual information, you've made a mistake. Now let's do an example. We'll take the same set of comments that we used earlier and compute the mutual information between a word such as hate and the sentiment positive or negative. The probability that a comment is positive is just the fraction of positive comments, which is 6,000 out of 8,000, and similarly 2,000 out of 8,000 for negative comments. The probability that hate occurs in a comment is just the ratio of hates out of the total of number of 8,000 comments, and similarly the probability that hate does not occur. The joint probabilities are a little more tricky. They're a little different from the conditional probabilities that we had earlier. For example, the probability that hate does not occur in a positive comment is, well, it's all the positive comments, that is 6,000 of them, but we divide by the total number of comments because this is the joint probability rather than the conditional one. In this case, for probability of hate, it doesn't occur in the positive comment, so we have to smooth it by just making the value 1 over 8,000. And similarly, we can compute the probability of not hate in negative comments and the probability of a hate in a negative comment. The mutual information between the word hate and the sentiment plus or minus is obtained by plugging into the formula, and you have 4 terms in the formula, one for hate plus, hate not hate plus, hate minus, and not hate minus, and the result is that we get the mutual information between hate and sentiment is 0.22. Well, is this good or bad? Let's check another word, the word coarse. It occurs in all the comments, so the probability of coarse is just 1. And the probability of not coarse is actually 0, but we smooth it by making it 1 over 8,000. The joint probability of coarse for positive comments is just the fraction of positive comments because it occurs all positive comments. In fact, it occurs in all comments. And similarly, the probability of a coarse in negative comments is just the probability of negative comments because it occurs in all comments. And not coarse doesn't occur, so again we smooth this. The resulting mutual information is 0.003. So what this is saying is that a word like coarse, which occurs everywhere, is not able to tell me anything about whether a sentiment is positive or negative. Quite obvious, but let's change the problem slightly. Let's now look at the case where these two comments don't actually have the word coarse. So we've just reworded them a bit. For coarse, now we have different values because coarse occurs only in some of the comments and not coarse occurs in these 1400 comments. The joint probability of coarse given a positive again changes. It's not all the positive comments, it's just 5,000 out of the 6,000 positive comments have coarse because you're removing these 1,000 comments that are positive and don't have coarse. And the probability that not coarse occurs in a positive comment is exactly this 1,000. So you get these values. Now the value of mutual information between coarse and sentiment is a bit bigger than before, but still much smaller than 0.22. What this tells us is that coarse is still a poor determiner of whether or not a comment is positive or negative. Something which is intuitively obvious to us. What's interesting is that using mutual information, a computer can determine such facts from examining vast volumes of data.